Welcome back for equations of a plane. As you can tell, I decided to break this into two videos, right? So first one was equations of a line, and this one will be equations, and I'll abbreviate, of a plane, right? And we have a diagram here to my left, might be your right. Now for the equation of a plane, we're going to need two things. The first should come as no surprise. We're going to need a point, right? So we're going to have a point on the plane. And we'll just say this is going to be x naught, y naught, and z naught. Now the next thing we're going to need is what's called the normal vector, denoted with an n. And we'll say this has three components, right? It's a vector, so we'll just say, we'll leave it arbitrary, a, b, and c. And again, this is what's known as, just so we have a description, the normal vector. Normal. And what it means to be normal is that it's going to be orthogonal to the plane, right? Orthogonal to plane. And that's the entire plane, meaning if you chose any vector on this plane, n, the normal vector, would be orthogonal to it. Now, what we're going to do now is we're going to construct an arbitrary vector. I gave you a point on the plane. I'm also now going to pick an arbitrary point. We'll define it as P. And we'll just say this is x, y, and z. And that should mimic what you see in our visual over there. Now, what we want to do with both P and P naught, right, are create position vectors, right? So R naught will be equal to x naught, y naught, and z naught, where P will be R, right? So these are both drawn from the origin x, y, and z. And so in this case, right, if we create a vector going from P to P naught, let's go from P naught to P, actually. Right, this is going to give us R minus R naught. And we'll group this together. Right, and now let's write out what this R minus R naught is. So let's go ahead and expand this. What is R minus R naught? Well, R minus R naught is going to be the vector, which is x minus x naught as our first component. Maybe you see where this is going. Y minus y naught, and z minus z naught. Awesome. Okay, now what did we say, right? So how are we going to use our normal vector to construct the equation of a plane, right? Because this is all abstract so far. What we know is that it's orthogonal to the plane, right? Which means it's orthogonal to any vector on the plane. And what did we just create was this vector. So we know that if these two things are orthogonal to each other, then it must be true that their dot product is equal to what? It must be equal to 0. Right? So let's just expand this out fully. The dot product would be A times x minus x naught plus B times y minus y naught plus C times z minus z naught is equal to, and what did we say? These are orthogonal to each other. So if we take the dot product of two orthogonal vectors, right, and we expanded it out, this is going to be equal to 0, right? So that's what's being shown over here in our visual. We have a P naught that is on our plane. We chose some abstract other point on our plane, and we constructed a vector. This constructed vector is this R minus R naught, right? Which leads us to x minus x naught, y minus y naught, z minus z naught. And we know that if this is an arbitrary vector, or an abstract vector there, and we take the dot product, it should be equal to 0. right? So taking the dot product between the two, we end up with this nice equation of a plane. So essentially, if we are given the vector, right, the normal vector ABC, right, it's very easy for us to jump straight to the equation of a plane, right? And we have our point x naught, y naught, z naught. We'll put like a squiggly under it so we can see it. Right, very easy for us to denote this, right? We can skip all the other hard part really once we understand the construction of it and just use these two pieces of information to jump straight to an equation of a plane. So in our next part of our video, that's what we're going to see. We're going to go through a couple different examples on if we're given a point and a normal vector, or if we're given a point and two other vectors, right? There's a way to construct the normal vector if it's orthogonal, right? And we'll go through both of those examples in the next part of the video. So I will see you then. Now that we understand the construction, right, of the equation of a plane, let's actually get into some examples. But I want to remind ourselves of what the equation of a plane is in case we didn't copy it down, right? So let's say we have some normal vector n denoted with a, b, and c, and we have some point. I'm not going to, I guess we'll write it down. Let's say we have some point, and we'll put p naught, but it's denoted by x naught, y naught, z naught. Our equation is as followed. We'll write it across the top here. We have a, right? This is coming from the dot product with the vector that we constructed. X minus x naught plus b times y minus y naught plus c, z minus z naught is equal to 0. Okay, so now we have that all written out. Let's go ahead. We're going to go for example 1. So we'll say example 1. Let's do an easy one to start off with. If I give you a normal vector, so let's go ahead. I'm going to give you a point and a normal vector. We'll say a point here is going to be 2, 5, -7. Let's close this out. And our normal vector, I'm just going to give it to us, will be equal to the vector 2, -1, 5, right? So if this is given to us, we can immediately jump to our equation, right? There's no reason to put some extra steps in between, where our A, B, and C, right, according to us, are right here. So let's just write this all out. We'll write it over here. We have 2 times x minus our first 2 plus b, and this is -1, so I might have messed up here. We'll just leave it as a -1 for right now, times y minus 5 plus, nope, let's get ahead, plus 5, z minus -7, so plus 7 is equal to 0. Now, we don't want to leave it just like this. This doesn't look great. Typically what we want is our x, y, and z on one side and the rest of the numbers on the other side. So let's just go ahead. We just need to distribute, right? And we can get rid of that -1 that's hanging out there. So we have 2x minus 4 minus y plus 5 plus 5z plus 35 is equal to 0. And I'm going to underline everything that we want to move to the right-hand side. What do we have? We have a -4 plus 5, so that's a +1 plus 35. So we now have a plus 36, and if we bring it to the other side, right, it's going to be a minus 36, so we'll just write it over here. Right, so one more time, -4 plus 5 plus 1 plus 35 plus 36. Drag it over to the other side, minus 36. And that leaves us with 2x minus y plus, and I have a big gap here, but that's, we'll make a big z, 5z. Right, so example 1, not too bad. If we know the equation of a plane, we're just plugging it straight in. We should see a visual over here of what our plane looks like, and we can go straight right into just plugging into the equation. Now let's come up with one that's a little bit more difficult. So we'll draw a line here to give ourselves some space. What if I give you 3 points? Right, if I give you 3 points, we can define a plane with these points. So let's go ahead. I have P, and we'll say P is going to be 1, 3, 2. I'll give you Q. We'll say Q, so we'll put a Q is going to be, what do we have here? 3, 0, negative 1. And we'll put R right below just to utilize our space. R is going to be 5, 2, 0. Perfect. Okay, so if I give you 3 points, right, can we come up with the equation of a plane? Well, what do we have? We definitely have a point. We have 3 of them, right? So that takes care of that. We can use any of those. But the question is, how do we construct a normal vector? Right, well, what do we know about the normal vector? That it's orthogonal to all of the vectors, right, in the plane. Well, what do we have? We don't have any vectors, but we can form some, right? As of right now, we just have points. So let's make some vectors. Let's go ahead. Let's construct them here. We have PQ. And this is going to be equal to, right, I'm going 3 minus 1. 2, 0 minus 3, negative 3, negative 1 minus 2, negative 3. Let's go ahead and construct now. We'll go PR. So we'll say P to R. So starting at R and subtracting 5 minus 1, we have 4. And I'll move out of the way. Actually, I'll move this way. 5 minus 1, we have 4. 2 minus 3, negative 1, 0 minus 2, right? Negative 2. Okay, so now we have these 2 vectors. How do we find, if we're given 2 vectors, right? We just learned about this in our prior video. How do we find a vector that is orthogonal to both of these? Well, what do? We do the cross product, right? So let's go ahead, we'll do the cross product. So we'll write our IJK. We'll fill it in with our vectors, 2, negative 3, and I'm going to go faster through this because we should have decent practice at this point. Right, so filling this out, right, we can come up with our normal vector, and we'll write it over here. So we'll say n is going to be equal to, right, the normal vector. Well, what do we have? If I want my first component, I block out my first row. I have negative 3 times negative 2, so 6 minus 3, so this is 3. Now be careful because we need to remember that when we get to our second component, right, the sign switches here to a negative, so we'll already add that in. Now we're blocking out our second column. We have negative 4 minus a negative 12, so negative 4 plus 12, positive 8, but we already have our negative sign, so 8, negative 8. And last, block out our third column, negative 2 minus a negative 12, so negative 2 plus 12, positive 10. Awesome. So now what do we have? Well, we have our normal vector, and we have 3 points. You choose whichever one you want. Right, so I'm going to have to get a little bit lower here. Maybe I'll write it right below. Yeah, that should be fine. Right, so we'll start off, right? We're going to take our equation of our plane and fill in the blanks. So we have A is equal to 3. Let's go ahead and draw a line here. I'm trying to utilize all the space we can. So we have 3 x minus, pick any point you want. Let's just go ahead. Let's use one of the ones with 0 in it, right? You can choose any one. I'm going to use R. So x minus 5 plus, actually we have a negative. I did it again, but we'll use ugly notation till we get there. Y minus 2 plus 10, and this is why I chose the 0 one, right? That's a 0, so it's just going to be 10z minus 0, or 10z is equal to 0. Awesome. And now what are we doing? All we're doing, right, is simplifying this, making this look a little bit nicer. What do we have? 3x. So we'll do 2 more steps. We're going to have just enough room here. 3x minus 15. We have minus 8y plus 16 plus 10z is equal to 0. And let's go ahead, underline our like terms, right? We want to keep the x, y, and z on this side, but we do have a minus 15 and a plus 16, so plus 1, which means on the other side, it just becomes a minus 1, and we're left with 3x minus 8y plus 10z is equal to, and we barely squeeze it in, -1. Perfect. Right, so 2 different examples here. Right, again, the first one, obviously, I think the easier of the examples. Right, if I give you the normal vector and I give you a point, right, it's as easy as just plugging straight into our equation. We do want to know where this comes from, so watch the prior part if you skipped over it. After we've done this type of example, what if I just give you points, right? So 3 points is enough to define a plane. That's not how we want to do it, because it won't be that efficient. But if we can construct 2 vectors, which we can do very easily, right? From our intro to vectors video. Once we have our 2 vectors, we know how to construct a vector that is orthogonal to both of these vectors using our cross product, right? Which is coming from the determinant. Again, something you'll talk about more in linear algebra. We construct, right, doing the cross product, we come up with our normal vector, right, the perpendicular vector, using our perpendicular or orthogonal vector, right, our normal vector, and any point, right, P, Q, or R, you could have tested them all, you would have had the same equation here. So we ended up with 3x minus 8y plus 10z equals -1. Hopefully the visuals over here help as well. We have one more example coming up. We'll talk about the angles between planes, very similar to angles between vectors. We're just using slightly different concepts because of the normal vectors. So I will see you in that example. Thanks, guys. Welcome back for our final example. I thought it was an interesting case. So we're going to look for the angle between 2 planes now. Right, so I'm going to give you 2 planes. You'll see some sort of visual over here so you can get an idea of what's happening. But let's have the 2 planes. We'll say x plus 2y minus z is equal to 1. And we'll do -x minus y minus z is equal to 0. And the question we want to ask ourselves is, are these parallel? Are these perpendicular? Or are they neither, right? Are they still intersecting, right? Is there some angle that we can create? So the first thing we can do is we can look to see if they are parallel. All right, so the first thing that we'll do is let's just go ahead and we're going to write these as their normal vectors. Let's use a different color. So their normal vectors, we'll say n1. We'll say this is 1 here and this is 2. So n1 is equal to, well, what are the slopes here? We have 1, 2, -1, and we have n2 is equal to -1, -1, -1. Right, so if we want to find the angle between these 2 vectors, we have a couple of different ways we can do it. We're going to use the dot product formula. We'll get to it in a second, but one quick thing that we can immediately notice, right, is if these 2 were parallel to each other, right, they should be scalar multiples of each other, but we can see that's not true, right? They're not scalar multiples of each other, so my guess is we can get rid of that, but we'll go ahead and confirm that by computing the angle, right? So let's go ahead. We know that cosine of theta, right, so this is coming back from our dot product days. We have cosine of theta is going to be equal to, in the numerator, the dot product of our vectors. In this case, there are normal vectors. Divided by the magnitude of these normal vectors. Perfect. I'll give you a second to copy down. Right, so now we just got to compute this. Right, so let's see what we get. Well, the dot product, right, let's just write this over here. We'll break it up into pieces. Ooh. So we'll do n1 dot n2 is going to be equal to 1 times -1, -1, plus 2 times -1, -2, plus -1 times -1, 1. So what do we end up with? Just -2. Okay. What do we need? We need the magnitudes now, so we'll find the magnitude of n1. This is going to be the square root of 1 squared, 1, plus 2 squared, 4, plus -1 squared, 1. We end up with root 6. And we will do n2, same exact way, will be equal to, what do we have? All ones across the board, right? So, I mean, -1 squared plus a bunch of ones, so this is just going to be root 3. Okay, now this does end up simplifying, right? So what do we end up having? Let's go ahead and we'll write it out here. We end up with cosine of theta. Where should we write this? Let's write it over here, right next to our cosine. We have cosine of theta is going to be equal to n1 dot n2, -2, over magnitude of 6. I'm going to rewrite it as such. Times the magnitude of 3, right? So this should help us see the simplification. All right, so this ends up simplifying to, ooh, no, that's okay. Let's use a different color. Wipe that up. Let's end up simplifying this to, so this is going to simplify. 2 over root 2 is going to simplify. We still have the negative sign up here, and this is going to be a root 2 over 3. All right, so now if we want to solve for theta, right, we have to do cosine inverse on both sides, right? So we end up with, and I'm going to end up going over here as well, theta is going to be equal to cosine inverse, right, of negative rad 2 over 3. And this ends up being about 118 degrees. 118. However, right, if you're looking at our visual over here, we see the planes rotating. If these planes intersect, which they do, they're not parallel, they're not perpendicular, they do intersect. But as you're staring at this rotation, you'll notice obviously the intersection, there's 2 angles that are created, right? And we define by the acute angle, right? So if there's an intersection between these 2 planes, right, we're going to have 2 angles that are going to be supplementary. They add up to 180. we want the one that's going to be the acute angle, or the one that is less than 90 degrees, right? So in this case, our answer for the angle that is formed between these two planes is going to be 100, and let's draw a line here. This is going to be 180 minus 118 degrees, right? Which gives us what? This gives us our final answer of 62 degrees. Awesome. Okay, so one more time, we'll do a quick walkthrough. Again, hopefully this visual helps, right? Again, there's the two angles that are formed when these planes intersect. We want the acute angle. So in this case, we got 118, but we know the supplementary angle that goes along with this is going to be 62, right? So I gave us some equations of planes. We should write them out as their normal vectors, right? And we can now find the angle between them using, right, this theorem that we have from a few sections ago when we went through dot product, right? Computing the dot product of n1 and n2, we had -2. Computing the magnitudes, √6, √3. We made some algebraic simplifications with a little bit of a smudge here, right? We ended up doing our cosine. We had 118 degrees. And again, we define, right, the angle between two planes as the acute angle, right? So instead of the 118, we wanted the 62 degrees, right? So hopefully this was helpful. If you have any questions, suggestions, let me know. Other than that, I will see you guys in class. Thanks, everyone.